attitude essential for quality research. We look forward to your comments, and the YouTube chat panel will be open to receive your questions. We'll try to take them up at the end of the session. Now, to delve into a totally new way of thinking for how to put together chemical molecules, we have with us a very special guest today. I would request Director BITM, Mr. V.S. Ramachandran, to introduce us to him and initiate this discussion on controlled chirality. Over to you, sir.
Thank you, Aditi. Good afternoon and a warm welcome to BITM online lecture series, the Science Nobel 2021. Today is the third day, highlighting the importance of this year's Nobel Prize winning work in chemistry. We are honored to have with us today Dr. Nitin Chattopadhyay, Professor, Department of Chemistry and a former Dean, Faculty of Science from Jadavpur University.
Again, enter screen. Sure. I'm happy to be here, being a part of this series of 3 lectures addressed to the Nobel Prize 2021. The first one was on physiology and medicine. Second one, these two are already over. Second one was on physics, and obviously the last one is the chemistry. So let me first disclose that I'm not here to describe the Nobel work. I'm not capable of doing that too. Rather, what I would address or how I would try to do is I try to make the surroundings, how one can go ahead for quality research. It may not be at the Nobel level, of course, that is the highest level of research, but still, how can quality research be achieved in our own way? Okay, this is me. Please don't hesitate at any later time to contact me for any reason at this email, and this is my mobile number. Okay. So, how do I organize this entire talk of maybe 50 minutes or 45 minutes, whatever it may be? As I already told, I will not go into the detail of the Nobel work actually, but I will just move around it. So, the Nobel Prize in Chemistry 2021, of course, I will give a little bit information on it. Then, as Aditi already told, that this year's Nobel is basically on catalysts. That means we are addressing to 2 different things. So one is the molecule. So I will discuss a little bit on molecule and their characterization, and obviously catalyst and mechanism of action, addressing towards the students who are attending this meeting. Then the more important thing is research attitude. What are the essential criteria for anyone to be a quality researcher? I may not say good researcher, but quality researcher at least. And if time permits, I will just show you a glimpse of research from our own laboratory. Only the essence of those things. So this year's Nobel Prize in Chemistry has been awarded to Dr. Benjamin List of Max Planck Institute for Coal Research, Mulheim, Germany, and 50% share goes to David Macmillan of Princeton University, USA. So they have the equal contributions on this year's Nobel Prize. Now, what is the basic topic of them? Interestingly, both List and Macmillan, they independently published 2 independent works in the same year, 2000, that means 2000, in JACS, Journal of American Chemical Society, one of the most prestigious journals in chemistry. And their works were quite in the same area, and so they were chosen together for this year's award. And the phrase or topic that they developed, the Nobel Committee developed, goes like this: Enamine and Iminium ion mediated organocatalysis. This is important, organocatalysis. Okay, so these are some photographs. This is some official declaration. So this will be there in YouTube, and who are interested, they can just go to read them if they are interested. Now, so the topic for this year's Nobel is Enamine and Iminium ion mediated organocatalysis. This immediately gives us two important items, because this is catalysis. So catalysis is connected to two terms. One is molecule and the other one is catalyst itself, or catalysis, the process, the method. What is a molecule? That is, you see, as I consider in any subject, in any topic, the first question should be, what is that? So what is a molecule? Everybody knows. A molecule is an electrically neutral group of atoms joined together by chemical bonds. Whatever may be the types of chemical bonds, electrovalent, covalent, coordinate valent, it doesn't matter, chemical bonds. And examples, plenty. Oxygen, methane, caffeine, DNA, protein, etc., innumerous number of molecules of varieties of types. But in relation to this year's Nobel Prize, this category of molecules known as asymmetric molecules are especially important. What is an asymmetric molecule? Let us consider with a very simple molecule. A carbon molecule, we all know that carbon is tetravalent. So this is connected to 4 different atoms or groups, A, 1, 2, 3, and 4. So maybe we can place this as this molecule, okay? And if we put a mirror, we can get the mirror image of it. Now, interestingly, asymmetric molecules, for asymmetric molecules, these two mirror, the original one and the mirror image, they are not superimposable. This is very important. And that leads to a different types of molecules, as they will be called, and they are called asymmetric molecules, not symmetric, asymmetric molecules. Now, a molecule to be asymmetric, the 4 terms should be different. 4 attachments should be different. Okay. Now, how do we represent? Okay, there are standard things in books you will get everywhere. And the miracles of these molecules come from their importance in medicine. These molecules are termed in terms of some Latin words. Sometimes they are called R, some molecule, like maybe R cetrizine or S cetrizine. R comes from Latin word rectus, right, S sinister, meaning left, and another pair of words, dextro, also the source is Latin. Dextro means rightward rotating, and levo means leftward rotating. So cetrizine, you all know, most of you know that cetrizine is a very common medicine that we often use to treat against allergy. Okay. So the speciality of these asymmetric molecules towards their action on or as medicine is very important. Sometimes the total collection of R and S, or sometimes this is called D or L, they work simultaneously to combat against the disease to the same extent. But there are plenty of examples where one form, one configuration may be a good medicine, while the other configuration acting as a poison for the human body or maybe any living being. So in that sense, this is very, very important to segregate them, to isolate and to collect only the configuration, maybe R or S, that is suitable for our treatment or for our requirement. Okay, the mixture, as it is called racemic mixture, will not do, right? Recently, cetgene, the full name is cetrizine actually. Anyway, cetgene is being replaced by L form of cetrizine to treat against allergy. Okay, how are these different configurations formed? Say, for example, this is the starting material or originating material, reacting material, and some other group is joining to this carbon, because this carbon is having this double bond here, C double bond. So cyanide may come from top, and this goes there, and H is joined. So we get some form of this OH and CN. Okay, tetravalence is maintained for the carbon. So this CN can either come join this unit from top, giving one configuration, or it may also come and join this group from the bottom, giving another configuration. One being R, the other being S. I don't know which one is which. Okay, so this is the important thing. Now, why this asymmetric synthesis and asymmetric molecule gets special attention or special coverage or special weightage for this year's Nobel? Because this year, the Nobel laureates, they have discovered a new type of catalyst. I'll come to it later on. They preferably prepare only one form of these configurations, two configurations, almost quantitatively, maybe 95% enantiomeric excess or 97%, something like that. So this is the specialty. And let me repeat again, the two forms, one may be friendly to us, the other may be poisonous, and it happens like that. Okay, so coming back again to the works of Benjamin List and David Macmillan, the title, I'm repeating again, Enamine and Iminium ion mediated amine. So this is N or in, and this is amine. So enamine. And this was the work of Benjamin List. And iminium ion based reaction was shown by Macmillan. So what is iminium ion? Actually, this is the imine. Okay, this is amine and this is imine. So imine, and you add R4 plus, so it becomes iminium ion. So these two, they constitute this year's Nobel. Okay. Now, to give an example of this thing, particularly enamine, proline is a protein, you know. Proline can both activate carbonyls in aldol condensation reaction. So this proline can activate carbonyls, reducing the activation energy. I'll come to it later on. And can control the reaction geometry. That means whether it will result, or it will give rise to R product or S product, right? Now, quite some time back, Richard Feynman, a physicist, Nobel laureate of course, he made a very fantastic, very nice statement. And what did he say? Everything that living things do can be understood in terms of the jiggling and wigglings of atoms. So this is the basic thing. So whatever we do, or anything does, is basically the movements of atoms, and in some cases molecules. Okay. So we have different types of molecules, and also we have some aggregated units known as molecular aggregates, or sometimes they are called self-assembly. Sorry. So the examples are like micelle. What is a micelle? If you take a surfactant-like molecule having hydrophilic head, having love towards water or protic medium or polar medium, hydro means water, hydrophilic head group and hydrophobic tail group, some aliphatic chain. So if you just go on adding this molecule in aqueous solution, after a certain concentration known as critical micellar concentration, what happens? Initially they were in random motion, in random arrangement, but after a certain concentration, as I called CMC, critical micellar concentration, to reduce the energy or to stabilize, what do they? They self-aggregate, they self-associate. They aggregate in the form, in the shape that these hydrophilic head groups, they make the boundary. So it makes something like a football, spherical or sometimes cylindrical also. So let us consider spherical. So the hydrophilic parts or ends will constitute the surface, and the hydrophobic parts, they will stay happily inside because there is much less of water inside. Now what is the use of it? This can provide different environments. Like this is polar and this is non-polar or apolar. So what happens? Most of our drugs or medicines, they are hydrophobic in nature. They come from our organic molecules, most of them. So what happens? They are not very soluble in water. So we cannot take sufficient or required dose of medicine if we want to, or if we try to take it naked. So what do? We put it inside micelle, because this is hydrophobic. So the organic molecules, they very happily go into this, and so this becomes a carrier. So micelle becomes a carrier. Okay. So this is the micelle, and similarly we have reverse micelle also. In this case, in case of reverse micelle, the bulk medium is oily medium, and you see these head groups, the hydrophilic head groups, they are now concentrated inside, and these hydrophobic tails are outside because outside is oil, they are loving. Now how does this unit get stability? You put a very small amount of water, so they are stabilized. You see these red ones are water, so this is called reverse micelles. Okay, this is just the reverse form of this micelle, because here outside medium is water, here outside medium is oil like thing. Then also we have cyclodextrin. Cyclodextrins look like these truncated buckets. Okay, glucopyranose units are there, and then 6 of them or 7 of them or 8 of them, they just assemble, self-arranged, self-aggregated. They are self-aggregated to form this thing. What is the speciality of this cyclodextrin? Based on 6, 7 or 8 molecular aggregates, or known as alpha cyclodextrin, beta cyclodextrin and gamma cyclodextrin, they form something like this truncated bucket. And interestingly, these outside rim regions are hydrophilic because there are so many OH groups, but this inner side, inner cavity is, they behave like hydrophobic environment. So this is another carrier of drugs. Okay, so you can take the drug or encapsulate the drug inside it, and this whole entity will go to the target where the drug should reach. Similarly, we have the molecular aggregates called lipids. Here also you see, this is the polar head group, this is non-polar, this hydrophobic tail, and then this is in the reverse order. So here head group, tail part, head group. So basically a double layer. So sometimes it is called lipid bilayer, and this is the basic structure of our cell membranes. Okay, so this forms basically the cell membranes. Okay, then also we have some molecular aggregates that maybe 2 molecules just stay in coupled mode, and they behave as a unit, as a singular unit. Okay, not really molecular shape or molecular form, but they work as a unit, single unit. Okay, now, by now we know what are molecules. Now, when a molecule is synthesized in the laboratory, the next step is characterization of it. So how do we characterize? It is the spectroscopy that helps us. Interestingly, spectroscopy is a fingerprint technique. So like my fingerprint cannot match with anyone's fingerprint in the world. So it is absolutely the same thing. So to cut the story short, there are different types of spectroscopy that we use, like using radio frequency in NMR, ESR, then microwave when we get this bond length for small molecules, of course. For big molecules, it's very difficult and it becomes useless in that sense. Then IR or infrared to characterize what are the functional groups are there, or if there is single bond, carbon-carbon single bond, carbon-carbon bond, or triple bond, something like that. And then UV visible spectroscopy, which is commonly called as photochemistry. And you see, this is the basis of existence of living creatures on the universe, because photosynthesis uses this UV visible spectroscopy or photochemistry. And without this photosynthesis, nothing can exist as living being. And so far as the characterization and structures of the molecule is concerned, X-ray is very important, and it gives the crystal structure very clearly. Okay, so these are the things, basic things that we use. There are some other modern techniques known as high resolution mass spectrometry, cryogenic electron microscopy, transmission electron microscopy. In short, this is called TEM. Similarly, SEM and AFM, corresponding to scanning electron microscopy, atomic force microscopy, and interestingly, single molecule spectroscopy. So basically, nowadays people can locate the single molecule. Of course, they cannot see the molecule. They cannot identify what are the atoms they are. That's not yet possible. But from optical parameters, these single entities can be isolated and located. They can be studied. Their properties can be studied. And this is very important. And Wedgig and Hell, they got the Nobel Prize in 2014 for their discovery of single molecule spectroscopy in the year 1989. Okay. Now, after getting some information, qualitative information and preliminary information on molecules, what is catalyst? What is catalyst? Catalyst is a substance that increases the rate of a reaction without itself undergoing any permanent chemical change. So you add at the beginning catalyst, and at the end of the reaction, you get back the catalyst. But in between, of course, it goes into the reaction, but ultimately or eventually at the end of the reaction, it comes out again. So that is the catalyst. Interestingly, before 2000 or till 2000, we had the idea that catalysts are of two categories. One is metal or metal related, metal associated. The other one is obviously biocatalysis or enzymes. But the important papers of List and independently of Macmillan in 2000, they conceptualized the area of organocatalysis. So they discovered and they put forward the proposition that not only the metals or metal related things and enzymes, they are catalysts. Simple organic molecules can also act as important catalysts, and they stimulated its development. And now you see, organocatalysis constitutes the third pillar of catalysis. The first one is this, second one is this, and third is the organocatalysis. Okay. Now, asymmetric organocatalysis has its special relevance for the formation of a precise, maybe L or dextro or levo entity, or maybe R or S entity, one particular, not just 50-50. So as in that sense, asymmetric organocatalysis provides a precise new tool, of course new tool, a precise tool for construction of asymmetric molecules. This is very, very important because quite often, in many of the times, we need only one form of asymmetric molecule, not the other one, because if we get the other one, this becomes useless. Okay. So in a sense, this asymmetric catalysis, it complements biocatalysis. Okay. Now, some basic information about catalysis and catalyst. As I promised, I will not go into the very detail. The concept was first introduced by Swedish chemist Berzelius way back in 1835. Now, interestingly, catalysis contributes to more than 35% of world's GDP. You see, so heavy importance in world's economy. In the year 2001, in his Nobel lecture, Ryuji Noori, he told, advances in chemical synthesis and catalysis implies the sustainable technological development of a country. So catalyst is so very important for any country. Of course, as I said already, catalysts in biological systems, they are more known as enzymes. Now, what is the mechanism of catalysis? This is known. Catalyst lowers the activation energy of a reaction. Everybody knows. And in all the literatures, you will get a picture like this. Okay. This is potential energy. This is reaction coordinate, meaning the progress of the reaction as we go right. As we go to the right side, this is the product, final product, and this is the reactant. But the important message that I want to percolate to the youngsters is that these pictures are incorrect pictures. They are incorrect diagrams because this picture is really some sort of abbreviation. You know, this is basically a combination of most potential energy curves of the reactants as well as the product. So now we know that most potential energy curve is like coming down and then going like this. So this is the most potential energy curve. Okay, let me repeat. So starting from here, maybe it goes down and then comes over here. So this is the most potential energy curve for the reactants. And you just couple it to the most potential energy curve of the product. And then you combine. So basically you get this entire diagram. But obviously, this cannot be flat one, this cannot be flat one, because this is the well. So although almost all the books, all the literature, they contain this thing, but please remember and accept that these figures are incorrect. So I would request all the youngsters to follow that this part should be should show some sort of curvature like this. Okay, here also. Now, okay, we know that if we use catalyst, then this activation energy from here it comes down. Then what is the mechanism of action of inhibitor? Inhibitor in some older books, they were termed as negative catalyst, but this is conceptually this term is erroneous. Okay, catalyst means something which can activate. So negative catalyst doesn't give any meaning in that sense. Inhibitor. So this restricts. In some books, loosely it is written that it increases the activation energy. Here it was saying that it lowers the activation energy, and for inhibitors, the mechanism in some cases they say that it increases the activation energy. But that is also again wrong. Because in case, if we accept that, okay, presence of inhibitor raises this energy, activation energy, fine. Then the reactants have the option either to follow the original path or to follow the higher activation energy path. So why should it opt for this higher one? It will simply throw it out. Like you are taking A and B to react in a beaker. You put some glass pieces some small pieces of glass, nothing will happen. The reaction will continue its own pathways. Okay, so here also the inhibitor should be ignored, so that cannot act as inhibitor, because inhibitor means it slows down the reaction rate. So what is the mechanism? So that is not the proper mechanism. The proper mechanism is very simple. Say for example, A and B, they are reacting, and you add C. Inhibitors are C that reacts with or that binds somehow loosely with A. So a part of A is being captured by the inhibitors, right? So that part of A or that portion of A, they are unable to undergo reaction. So when basically the concentration of A is reduced, if the concentration is reduced, then reaction rate is product of rate constant into concentration of the reactants. So when the reaction rate, when the reactant concentration goes down, obviously the reaction rate will come down. So that is the actual explanation. Okay, fine. Now this is important. What is the research attitude? Let me put forward some well-known and well-respected, well-accepted statements, quotes. This was given by Professor APJ Abdul Kalam. Dream. To achieve anything great, one has to dream. What is dream? Dream is not that you see in sleep. Dream is something that does not let you sleep. That is dream. Okay. Then another important thing is attitude. Attitude is everything in a person's life. How he explains it. All birds find shelter during a rain, but eagle avoids rain not by hiding him or itself under some shade. What does it do? But eagle avoids rain by flying above the clouds. And when you are above the clouds, no rain. So you see, problems are common to all, but attitude makes the difference. So we have to build proper attitude in us. Another example, another quote of Thomas Alva Edison. I haven't failed. I have just found 10,000 ways that don't work. This is called positive attitude. Okay. Then the known face, Ratan Tata, he says in one occasion, none can destroy iron, but its own rust can. Similarly, none can destroy a person, but his own mindset can. Mindset is simply the other word of attitude. So attitude is everything. Okay. Now, to do quality research, you have to have some education, you have to have some knowledge, have some idea. What is the objective of education? Getting some high marks and good certificates and mark sheets? No, dears. That is not the objective of education. What is the objective of education? If I ask the question, the answer comes like to enhance the capability of logical thinking on any aspect, on any subject, on any topic. So the objective of education should be to enhance the capability of logical thinking. And you know, this logical thinking is the basis of quality. So unless we have the power of logical thinking, we cannot be good researchers. You see, after getting the Nobel Prize, Benjamin List told in a press conference that when I first did the experiment, I didn't know what would happen. And I thought maybe it's a stupid idea or somebody has already tried it. But when I saw it work, I did feel that this could be something big. So this should be the attitude. Even if you don't find many optimistic or very optimistic on something, you have to try, and something big may come out of it. Important aspects of research attitude: think out of box and design your scientific problem in your own way, not just copy. Somebody in US, he has produced some new technology to react A plus B giving C, and I am just repeating the experiment by A plus B prime giving rise to C prime. That's not a great or path-breaking research. Okay, that's just incremental research. So think out of box and design your scientific problem in your own way. Translate science into society and vice versa. So you should replicate the thing into society, scientific concept into society, and you get or you convert this societal knowledge into your science. Give your best and never be happy with your best. So always try to improve your best. Okay, that should be the thing. The other and very important thing is stop giving excuses. We always love to give excuses for our own faults. So unless you stop giving excuses, you cannot go to any level. Qualities required for this quality research is hunger for learning, inquisitiveness, honesty and morality, tenacity, dedication, perseverance, self-aggression, so on and so forth. And let me give one example. John Goodenough, he won the Nobel Prize only a couple of years back, precisely in 2019. Do you know his age? At the age of 97. By the way, he is this Professor John Goodenough of University of Texas at that moment. He is the oldest one to receive Nobel Prize, okay, in history. Then another important thing, major part of quality research comes from your brain. So as I often colloquially say, 90 to 95% research is done here in your brain, and very, very costly instruments are required only to make your thoughts visible. They don't give something new out of them, out of the very, very, very costly instruments. They don't give anything. With their help, with the help of the instruments, you may make your thoughts, your ideas visible. That's all. So the main thing that you should concentrate on or look on is your brain. Okay. Let me give some simple research examples from our lab. Is it maximization of sensing, a learning from the society? As I told a couple of minutes back, we must learn from the society and we must give scientific knowledge to the society. So what is sensing? You know, most of you know, detection and or estimation of pollutants or analytes in solution or in maybe any material or even bloodstream, like arsenic and cyanide in water and potassium ion, sodium ion, copper ion in your blood sample, etc., etc. Okay. So to sense, what are the methods of sensing that do exist in the science? Liquid chromatography, potentiometry, capillary electrophoresis, etc., 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 so on and so forth. But fluorosensing is a new one, rather newer one, and this is very, very, very sensitive, called supersensitive. So presence of a very little amount of substance can be detected very precisely and confidently, reproducibly by using fluorosensing. Now there are two ways. One is, say for example, the sensor is having some emission, and when you add this analyte, the fluorescence intensity goes up. This is enhancement, fluorescence enhancement based sensing, or it may go down. So this was the original intensity or fluorescence intensity of the sensor, and upon addition of the analyte, this fluorescence goes down. Okay, this is quenching based sensing. Now what are the criteria that the sensor must have? Two, mostly two. One is selectivity, the other one is sensitivity. Selectivity, we have no control. This is just based on luck. We have to try. and error. That's it. But sensitivity, maybe we can change. We can modulate. Say, for example, a molecule is sensitive, but not to a good extent to some A. I may replace one H by CH3, and we try again, and we see that, okay, the sensing is more. We can again replace another group to see that, okay, now it's even more. So this is standard error method based on synthesis, but this is not so easy. But there is another very simple thing, modification of the environment. So this was our attempt. Okay, what is the thing? What is the approach? Very simple. Say, for example, in a city like Kolkata, some metropolitan city, you are a newcomer, so you are looking for to take some shelter, some apartment on rent. You want to take it, and there are plenty of apartments lying vacant, but the owners of those flats, they don't know that you need one. So he wants to give the flat on rent, and you want to hire it on rent, but you do not know. So the reaction doesn't take place. The process, the handshaking is not there. So what do? You approach a broker, and that owner of the flat, he also approaches the same broker, and your handshaking is done. So this is a societal learning that we learned, and we simply used it in science to get another JACS publication, Journal of American Chemical Society. As I already told, this is the mostly respected or highest respected chemistry journal. Anyway, what did we do? This is the sensor. Forget about some molecule, okay? And medium water, because our objective was to sense copper ion, because our bloodstream contains some amount of copper ion, and copper ion is essential. But if the dose is or concentration of copper is a bit higher, and then we are in trouble. We have skin diseases, and it becomes fatal. So what what is the problem in normal sensing? Concentration of copper lies in the micromolar region, and this sensor, we cannot use too much of it because that is organic molecule. So this is also problematic, maybe carcinogenic. Most of the organic molecules are carcinogenic, as a general information. So we cannot use it to a good extent. Of course, this is not soluble also in water. This is organic molecule. So at the best, we can have this sensor in the range of micromolar again. So micromolar copper ion and micromolar this AODIQ. So they are well separated. And this fluorescence quenching, that was our method of sensing. Fluorescence quenching means you excite the system, this fluorescence, and within this fluorescence lifetime, maybe 1 nanosecond, they have this dye molecule is there, and so copper has to come and interact so that this fluorescence goes down. That's very difficult because they are far apart. They have to come through diffusion. So it takes a long time. So what did we do? This is the owner of the house, and you are looking for the house to take on rent. Now we used anionic micelle as the broker. Why anionic micelle? Because our target is copper ion, positive. So as we have already shown that micelles are like spherical things, and micelles can be anionic, that means surface is negatively charged. It may be non-ionic, it may be cationic as well. But here specifically we chose anionic micelle, because if we take anionic micelle, more of negative charges are there, so copper ions will be coming, they will be close to this periphery, and this molecule, this sensor molecule is already on the surface of the micelle. Okay, so now they are in proximity. So you excite this molecule, this AODIQ molecule, the fluorescence is there, and very close to it, copper ions are there. So quenching is very, very, very efficient. So this quenching efficiency or sensing ability, we may call, is enhanced by more than 2000 fold. It was a massive enhancement. Okay. Now, as an extension of this powerful technique, we ask ourselves, is it possible to sense cation like copper by a cationic species? You see, if this be the molecular system, chloride is counter ion, so this is the fluorescing unit, and that is positive ion. Is it possible to use this phenolphthalein molecular system, that means the cationic part, to sense a cation? The normal answer is no, that is not possible, because this negative, this is positive and copper ion is also positive. They will come and then electrostatic repulsion. They cannot come in contact, so there will be no interaction. But we could sense for the first time in science, this is the first time in science that a cationic species can sense or really sensed cationic item like copper very efficiently, simply by using a broker. Of course, what did we do is we modulated or we played on this carbon chain, length of this carbon chain of the surfactants. Okay, that means we changed the surfactant systems or micellar system. That's it. Now coming to the other thing, I am not going into the detail to make you bored. Improve delivery of drugs to target and excretion of excess drugs from the body. You know, now for different regions, for different elements, we are used to take medicines, a lot of medicines. So they are essential, but at the same time, they induce some second order disorder. So we take again another new type of molecule drug, and we invite another problem. So it goes on. So the ways to get rid of drug-induced side effects, or at least to reduce the drug-induced side effects, as we thought, are two. Number one, to deliver drugs efficiently to the target, and two, this is a new concept, to expel adsorbed drugs from the body occasionally. This also I learned from the society. What do we do when our shirts or clothes get dirty? We just wash them. No? How do we wash? We give some detergent, we put it in a washing machine, or we disturb it in a bucket, and we wash it. So basically, we are injecting some, or we are providing some surfactant-like thing or detergent-like thing to take it out. Exactly the same thing. Now, while considering this drug delivery, there are basically two approaches. One is endogenous, and the other one is exogenous. Endogenous means the carrier carries the drug, and when the target region may be DNA, when the target is reached, the binding efficiency of the drug is higher with the target than with the carrier. So the carrier was carrying the drug. When the DNA is there, since the binding efficiency or binding affinity of this drug is more with the DNA, so it automatically goes there and this carrier becomes free. This is endogenous. And exogenous, in exogenous case, this carrier had stronger binding affinity with the drug. So even if it reaches there at the target, the drug is not released. Now we add some external stimulant. It is called stimulant. We add something else so that this structure is broken. And then this drug is in the aqueous medium, which is unpreferable. So immediately it goes there. So these are the two approaches. Let me give the schemes. So this is, as I said already, lipid bilayer. This is endogenous delivery of drug from lipid to DNA. This is the schematic picture only. So this is the schematic figure of this lipid bilayer, and let us consider that these drugs are bound. So this is the carrier, and DNA, when it goes there, since the binding affinity of the drug with the DNA is higher, so the drug is transferred and this carrier is made free. Okay. Similarly, micelles can also do the same thing. We carry the drug using the carrier micelle. When it reaches the DNA, since the binding affinity is more, so the drug is transferred and the carrier becomes free. These are all endogenous. But for exogenous delivery, what do we do? The carrier is taken as the micelle and the stimulant is beta cyclohexene. Let us go to the scheme. So this micelle is carrying the drug. It reaches or it comes in the proximity of DNA, but since the binding affinity of the drug with the micelle is more, it is not transferred. So what do? We put beta cyclohexene. This is by the way, beta cyclohexene is friendly to our health. So we put beta cyclohexene there, and it breaks the structure. Okay, and then this drug remains in water. Obviously, that is not a preferable situation, so it goes there, right? So these are the drug delivery systems. Now, what about drug excretion? Say, for example, I am a patient of hypertension. So for years, I have been taking medicine. So what is the fate of the medicine? They work okay, fine. My pressure is in control. But the thing is, excess drugs and used up drugs, they are trapped in the cell membrane. And eventually the concentration of the drugs become very high, and this makes system toxic, and even cancer may come out of it. So what do? So we have made some experiments. As I already told, cell membranes are basically lipid bilayer. So we started with lipid bilayer. You see excretion of adsorbed drugs from lipid membranes. So this is the lipid bilayer. That means this is the model of our cell membrane. So we are taking drugs, and these membranes are full of drugs now. Now, occasionally, maybe after a period of 6 months, I take maybe for 3 weeks some cyclohexene dose, and cyclohexene goes there and it takes most of the drugs. So that is a very simple thing. Now, okay, this is in vitro experiment. In the lab experiment, no problem. Is it really applicable to the real cell? So we also extended our study to real cell, living cell. What is that cell? Chinese hamster ovarian cell. And as a model drug, we took nylade, which has color. We use the confocal microscopy, etc., etc. Forget about all these things. I do not know if you can see. This is a living cell, and you see a nylade doped it. So you can see perhaps only the boundary is seen to have red dots. Nylade is red. That is why it is named nylade. So you can see perhaps these red dots. And then we added beta cyclohexene, which is visibly there, and you see the cell is now free of drugs. Okay? So that is a very simple thing and very clean thing. Now one may argue, sir, what's the benefit? Because beta CD is still with the drug and it is within our body. Now it cannot stay there, because beta CD, as I said, is highly soluble in water. It has so many wedge groups. So beta CD containing the nylade or any drug that goes out of the body by normal ejection channels of water, like urine, like sweat, etc., etc. So here I am. If you have any question, please go ahead. Thank you very much for your patience.